This is part 1 of 3 on the idea that acceleration of an object is parallel to the net force acting on the object. In this part, I'm going to teach you the head-to-tail graphical method for adding vectors. What do we do with a free body diagram once we have one? We model interactions with an FBD for the following purpose. It is to predict the acceleration of the object. That's what an FBD is for. Taking Newton's first law a step further, observational evidence informs us that interactions cause acceleration, and that more specifically when interactions are modeled as forces, which are vectors that can add up or cancel out, at every instant an object will accelerate in the direction of the instantaneous net force. Your acceleration and net force vectors are always parallel. Net force, recall, is the sum of all the forces acting at that instant. This idea is, this principle here is so important. I've actually discovered a representation of it in an ancient Japanese haiku from my studies of Shinto physics. Here it is. At every instant, an object accelerates parallel net force. Actual ancient Japanese haiku. To find the instantaneous net force, we need to be able to add the force vectors. So remember that a vector, and that's a quantity represented by two or more numbers, and two numbers in 2D, and they are the components of the vector. Here we'll model a force by saying that force F is a vector with components Fx and Fy. The force is a vector, but the components themselves are scalars. A scalar is a quantity represented by just one number. So the components are scalars. The magnitude of the force is also a scalar. Magnitude can be found, from the components using Pythagorean theorem. So these are scalars, individual numbers, but the components together, that collection, gives us our whole vector. So to figure out how to add vectors, let's first think of something you know how to do: add scalars. Okay, so here are three integers, 5, 6, and -3 that you could add easily. But let's look at a visual way to do it. On a number line, represent the number 5 as an arrow, starting from 0 and pointing towards location 5. So that arrow there, kind of like a vector, represents the number 5. Likewise, here's the number 6 represented with an arrow, and the number -3 represented with an arrow. We can add these three integers visually by starting with the first one and drawing that arrow pointing to 5. And then starting there, taking the tail of the next vector and sticking it at the head of the first vector. So there's 5, and then we're going to add the 6 to it. 3, 4, 5, 6, sort of lining them up head to tail, and then take the next one, the -3. Starting here, putting the tail of -3 at the head of 6, and going backwards 3. And having done that, we start from the very beginning of that chain of arrows and draw a resulting arrow from the very beginning to the very end, right here where our chain ended up, and we see the length of that is 8. That is the sum of those three integers here. The arrow we get by drawing from the very beginning of the chain to the very end of the chain. Let's take that visual method for adding scalars in 1D and transfer it to adding vectors in 2D. Here we've got a free body diagram with three forces acting on this object at this instant: force 1, force 2, force 3. We want to figure out what direction the net force will be so we can predict the acceleration of this object at that instant. From looking at the vectors, you can kind of make an initial prediction. Let's see, these are pulling upwards a bit, this one's pulling downwards a bit, that might kind of cancel. This one's pulling right, this one's pulling right, this one's pulling left, but not as hard. So I think overall we're going to have kind of a net force, something like that. There's my prediction right there. So our acceleration should also be roughly in that direction. That's the prediction, but now let's get the actual exact net force. We're going to use this head-to-tail method. Start by picking one of the vectors, F1 here, and draw it by itself. So it goes over 4 and up 4. So there's F1. And I'm going to take the next one, F2, and draw it starting at the head of F1. Tail of the vector is this end, head is this end. So F2 goes down 5 over 2. So starting here at the head of F1, down 5 and over 2, draw in F2. Then take the third vector, F3, that goes over 3 and up 2. So starting from here, over 3 and up 2, brings us there. There is F3. So we've created this chain of arrows lining them up head to tail like we did with these scalars up here. And now the result, the sum of those three vectors can be found by drawing the arrow that starts at the very beginning of the chain and ends at the very end of the chain. So from here to there, that arrow in red, that is the net force. That vector is the sum of those three vectors. And I'll highlight it to make it clear. There we go. That's the sum, points over 3 and up 1. And that then also, according to our ancient haiku, that sum will also be the direction of our acceleration. The acceleration of the object at that instant will be parallel to this net force. Okay, I've got an example for you to try out on your own. Here's another free body diagram. This one has 4 forces instead of 3, but the method works the same way. Just make a chain of those 4 forces, starting with one of them, and keep adding them head to tail, and draw the result pointing from the very beginning of that chain to the very end of that chain. I encourage you to make a prediction before you start, just from looking at these vectors here. Make a prediction of what the net force what direction it should roughly be, and then try out the method and test your prediction. Okay, grab some graph paper to help you out with this, and pause the video, and I'll reveal the result when you're ready. Are you ready? Okay, here it is. I've got F1 added to then F2, added F3, added F4. There's my chain. The result points from the very beginning to the very end. There's the net force pointing down and to the left. And of course, since at every instant an object accelerates parallel net force, that indicates that our acceleration of this object will also be in that direction, parallel to the net force at this instant.